Hi everyone and welcome. My name is Branko. I'm a creative roads manager here at MikroElektronika, and today I'm excited to walk you through a real-world embedded project, LoRa and Wi-Fi powered early warning system for earthquakes, floods and thunderstorms. Here is what the final solution is going to look like. This is the transmitter and it is fully up and running on Planet Debug. And why am I doing this? Well, it is all about natural disasters, which became our daily concern. But what I really want to show you is how to think and build like a modular embedded developer to start solving issues against natural disasters yourself. Okay, I will dive into a solution that is built around real-world sensors: earthquake click, water detect click, and thunder click. And I will combine all of those with LoRa 11 click for long-range LoRa communication. But beneath the hardware, this hardware is something deeper, a software architecture that is modular, scalable, and maintainable. So let's focus on the modular part. Each sensor is fully encapsulated. It does one thing and does it well. Well, okay, so this is the single responsibility principle, SRP. Okay, now let's switch to the scalable. Want to add more sensors? Just append another function and update the sensor list. And finally, maintainable. Easy to tweak, extend, and swap components without breaking other parts. I will show you how to approach this project methodically and professionally. First, you will see how to structure your code base into clear, maintainable modules. Specifically, I'm going to separate logging, connectivity, and sensors apart. Then I will use the convergence utility from the MikroSDK to convert sensor data to prepare sensor data for transmission in a format suitable for LoRa. You will also learn how to evolve clipboard examples. So instead of just logging data locally, you will start populating structured buffers ready for remote transmission. I will go further by cleaning up repetitive if-else blocks and introducing cleaner, more fault-tolerant patterns. On top of that, I will show you how to easily switch between transmitter and receiver roles, simply by toggling a line in the CMake build configuration file. And finally, you will see how all of these elements come together, combining multiple clipboards into a cohesive embedded solution that is not only the robust, but also easy to expand, maintain, and test. So let's jump in. Let me switch to the NECTO ID right now. Okay, let's take a quick look at the hardware setup behind this solution. It is composed of two main devices: a transmitter. This is the development board that you are currently watching, and a receiver. This receiver development board I'm going to show, but in the later stages of this webinar session. Okay, and both are built using the same core development environment. Each device is based on the Fusion for ARM version 8. Here it is. Okay, Fusion for ARM version 8. Perfect. Okay, this is a versatile development system equipped with microbus sockets and powered by a plug-in microcontroller card. Here is the microcontroller card. Okay, perfect, here it is. And you can plug in, plug out, just like that. Okay, and on the transmitter side, we have three sensor-based clipboards: earthquake click, water detect click, and thunder click. Here they are: earthquake click, water detect click, and thunder click board. Okay, alongside LoRa 11 clipboard for LoRa communication. And here it is, LoRa 11 clipboard. Perfect. Okay, on the receiver side, we also use a LoRa 11 clipboard paired with Calypso clipboard for Wi-Fi connectivity. Okay, from the software side, everything is developed and flashed using NECTO Studio. This guy over here, okay? Okay, this is our all-in-one IDE. It is powered by the MikroSDK framework, which handles clipboard drivers. Each clipboard is integrated via its respective click package, which you can see over here. Okay, here it is. Perfect. Storm and quake alert transmitter, storm and quake alert receiver. Okay, these are the software packages. Okay, let me just get back to the planet debug. Perfect. Okay, and those provide ready-to-use wrapper functions. To flash the firmware, we use code grip. This guy over here. Here it is. Here is the code grip device, which is onboard programmer and debugger device, and it is Wi-Fi capable as well. So we have it in the onboard version Wi-Fi capable, and we have it as a standalone Wi-Fi version as well. Okay. And finally, thanks to the Planet Debug, we can remotely run and test both the transmitter and the receiver devices directly from NECTO, without needing to physically connect the hardware to my laptop. Okay, let me switch to myself right now. Just give me a second. Okay, perfect. Now that I have explained the hardware section of this solution, now I'm going to explain the software section. I will walk you through this core logic of the solution right now. So I'm going to dive straight into the main.c file, the heart of this solution. Okay, let me switch to NECTO once again. Okay, perfect. I'm building a resilient environmental alert system that can operate in two modes: transmitter mode and receiver mode. Just give me a second. Okay, transmitter mode and receiver mode. Okay. In the transmitter mode, I'm collecting real-time data from sensors. So once again, earthquake, water detect, and thunder clipboards, and pushing it wirelessly using the LoRa 11 clipboard. Okay, in the receiver part, I'm receiving those packets via LoRa 11 click and then forwarding them to the TCP server using Wi-Fi with the help of the Calypso clipboard. Okay, this way I can detect seismic activity, water presence, and electrical storm intensity, and alert a remote endpoint over TCP UDP. Now, what happens in the application initialization? Okay, let's find that functionality. Okay, and here it is. Here is the application init functionality. This one over here. And what basically happens in the application init functionality? I'm initializing three core components here: logger, connectivity, and the transmitter logic. Okay, so in terms of the logger part, I can trace what's going on in the system via UART protocol. Okay, in terms of the connectivity, regardless of the transmit or receive mode, the LoRa 11 transmitter must be set up. Okay, and the number 3 part is the transmitter mode logic part. Okay, if I'm in transmitter mode, I'm initializing sensor boards. Okay, sensor init. Yep. Okay, after that I'm going to populate a function pointer array. Okay, and with hooks to each sensor's data acquisition function. So once again, I'm going to populate a function pointer array, this one over here, with hooks to each sensor's data acquisition function. This gives me modularity. I can later swap a sensor without changing main.c file. Okay. Now the next logical part is the question that needs to be asked, and that would be how application task works. Okay, just give me a second, and here it is. Here is the application task. Yeah, it's a little bit more of a functionality than the previous one, than the application init. Okay, so let's explain this functionality as well. Okay, the next logical thing I've got to explain is how application task works. Okay, I'm defining a state machine to control application flow. Okay, switch up application state. And I will start with power up logic. Okay, I'm going to power up the LoRa 11 clipboard. If LoRa 11 powers up successfully, I move to config example. Okay, here it is. Config example. Here it is. Okay. In config example, I transmit a single setup message. You can transmit whichever message you would like to. I have used the default one, this one over here. Okay. Then I move into the example state, which is my main data collection and transmission loop. Okay, here is the example state. From there, from there, in config example, I transmit a single setup message. Okay. In this state, if in transmitter mode, I'm going to definitely loop through each registered sensor. Okay, because of this for loop over here. So once again, if I'm in a transmitter mode, I'm looping through each registered sensor. Then I'm calling the data fetching function via sensor func logic. Okay, here it is. And finally, I'm transmitting that data using the transmit function, but with the LoRa clipboard. Okay, and here it is. I'm going to transmit the data buffer. Okay, and if I'm in receiver mode, I'm going to receive that data from LoRa 11. Okay, if I'm in receiver mode, I'm going to receive that data, and I'm immediately forwarding it over Wi-Fi using Calypso transmit. Okay, here is the Calypso transmit functionality. So once again, I'm going to use Wi-Fi capability to transmit data that I just have received, and I'm going to send for example, a Docker-based TCP server, which I'm going to demo for about 15 minutes, for example. Yeah. Okay, each loop is delayed a bit with delay of 500 milliseconds to manage timing between packets. And you may be wondering how to switch between transmitter and receiver modes. Well, let's see. I'm definitely going to switch to the CMake logic. So I'm going to search for the comment over here, and please do take a moment to read this comment. It is a very important one. Okay. Well, once again, if I'm using preprocessor macros in CMake to switch modes, for transmitter mode, I'm definitely going to stick with this line over here, and for a receiver mode, I'm definitely going to stick with this logic over here. Okay, perfect. This lets me use the same main.c file, but change behavior at compile time. No need to touch the source code. So once again, I do not need to touch the source code, the main.c file. I just have to switch the logic in the CMake file. Okay, and the final function that needs to be explained is the main function. And here it is. It is a simple function, but we have to explain it. Okay, I'm optionally calling pre-init for low-level platform setup. Here is the pre-init. So in essence, a clock configuration for some microcontrollers. I think this pre-init functionality is going to be called for some DSP microcontrollers, I think. Then I'm calling application init over here, and finally entering an infinite loop where application task runs repeatedly. This structure ensures my firmware stays responsive and continues to collect or transmit data indefinitely. And what I love about this structure, this whole example, this whole solution, is how clean and modular it is. The function pointers give me flexibility, the state machine gives me control, and the macro-based config lets me reuse the same firmware base for both the transmitter and receiver roles. By combining these sensor boards with LoRa and Wi-Fi, I'm effectively bridging local event detection and remote alert delivery entirely wirelessly. So once again, entirely wirelessly. Okay, now I'm going to switch to other logic. I'm going to take a moment to talk about one of the most important but often overlooked parts of embedded development: logging. Yeah, logging, once again, logging. When I'm working on a critical solution like storm and quake alert with Wi-Fi push, I need full visibility into what's happening on the system, from sensor readings to communication handshakes. This is where UART logging becomes absolutely essential. To keep things modular, centralized, and consistent, I'm introducing a custom logging abstraction in two simple files. And here they are. Just give me a second. Logging header file, and of course logging C file. Okay, let's focus on the logging header file. This header file defines the interface. Let me walk you through it. I'm including two core microSDK headers: the log header, obviously, and the board header. I need log header to access the microSDK logging functions, and I need board header for UART pin and configuration defaults. Once again, I need board header for UART pins. That's it. And then I'm exposing a global variable, this one over here. This allows me to use a single logger instance throughout the application, from main.c file to sensor and connectivity layers, without reinitializing or reconfiguring logging in multiple places. And finally, I'm declaring the function over here, logging init. That's the only API I need. A clean, single entry point to set up everything, which I definitely need. This interface is compact and reusable, and it aligns with MikroSDK's component-based philosophy. Okay, let's focus on the C file, on the source file of the logging logic. At the top, I'm including my own logging header file. No surprises here. Then I define the logger instance over here. This is where I'm actually allocating memory for the global logger declared in the header. And inside logging init, this function over here, I create and configure the log configure type structure. And after that, I call the macro log map USB UART. And this maps the UART transmit and receive pins for the USB UART, using board header as the source of truth. It's fully portable across Microbus dev boards. Then I initialize the logger, log init, over here. Finally, I send a welcome message, log init, this log info, sorry. That tells me, or any user watching the UART terminal, that the system has booted and is ready. Okay, and here is why I'm doing this. It decouples application logic from logging setup. So if I ever switch to a different logging backend, I only need to touch logging C file. Then it gives every module access to the same logger instance. I just include logging header file and you'll use log info. Yeah. And the final thing is it enforces a single centralized UART config, avoiding conflicts or redundant setups. And how this fits into NECTO Studio projects. In NECTO Studio, I'm often working across multiple layers: sensors, transport, and main loop. And if something goes wrong, I want to trace it fast. By calling logging init in application init, so in the application init, here it is, I'm setting the stage for full observability. Whether I'm debugging a failed sensor read or packet loss in LoRa 11, logging is my first line of defense. And one bonus tip for the webinar audience, for you guys: if you're using a dev board that doesn't expose the USB port by default, like some custom STM32 boards, make sure to check your board header file. You might need to redefine USB port RX pin and USB port TX pin. So let me explain it. Okay, logging. Okay, board header file. Perfect. And here it is. USB port transmit and USB port RX. Okay. And you might need to redefine USB port or receive and USB port transmit pins manually, or just replace log map USB port with your custom port mapping. Okay, so to wrap up, I'm using logging header and logging source file to keep logging portable, scalable, and debug friendly across my embedded application. Okay. The next thing that I have to explain is the sensors part. So once again, I'm going to explain the last section that needs to be explained: sensor logic. And this sensor logic is across sensor header file and sensor source file. So I'm going to show it to you guys. I don't need port header file, and this one, and this one, and this one. Okay, I'm just going to focus on this one, sensor header file, and sensor C file. Okay, just give me a second. Okay, I can start. In a real-world application, managing multiple sensors through clear abstraction is crucial. This project integrates 3 clipboards: earthquake click, water detect click, and thunder click. And this duo, this combo, sensor header file and sensor source file, these two, so sensor header file and sensors C file, are crafted to make all 3 sensors modular, reusable, and easily expandable. So let's begin with sensor header file. Okay, this is a header file that exposes sensor 1 init, then sensor 1 data, sensor 2 init, then sensor 2 data, and finally, logically, I'm going to have a sensor 3 init and sensor 3 data. 1, 2, 3. So the sensor 1 init is definitely for the earthquake logging, sensor 2 is for the water detection, and sensor 3 is for the thunder detection. Okay, now I have function pointer type as well, this one over here. And yeah, this one is perfect for dynamic sensor cycling or scheduling in larger systems. Okay, I have global driver instances as well, these guys over here, and those link directly to their implementation in sensors.c file for each clipboard. Okay, and now I'm going to focus on the sensors.c file, and I'm going to focus on the sensor number 1, and this sensor is the earthquake sensor. Okay, and it uses seismic intensity. Seismic intensity values to determine shock strength, and it reads from the I2C. This is why I want to switch I2C communication to earthquake click. Okay, so it reads from I2C, then interprets mode codes and returns human readable alerts, and the memory is cleared after each reading to avoid stale data. Okay, and okay, let's focus on the sensor number 2. Okay, and here it is, sensor number 2, this one over here, and it is water detect sensor. Okay, it simplifies flood or leak detection using a digital pin state, and it detects transitions using the WD state old and WD state, so WD state old and WD state, so water detect state old and water detect state, logically. Okay, and this one is ideal for rapid water level change alerts in homes, greenhouses, or industrial tanks. Okay, the last one is the sensor 3. Okay, and it is the thunder clipboard sensor. It is going to detect noise, disturbance, and actual lightning. And it extracts energy and distance of lighting with thunder gets storm info functionality. And here it is. Here is the information. Here is the functionality which is going to extract the energy and distance of lighting. Okay. And once again, why this matters in NECTO projects? In NECTO Studio, splitting sensors this way, so sensor 3 data, sensor 2 data, and in sensor 1 data logic. So splitting sensors this way means easier debugging, reusable templates, and modular expansion. Let's focus on the easier debugging thing right now. Each sensor logs and handles its own internal state. Number 2 is reusable templates. You can drop in a new clipboard, add init data functions, and you're done. And number 3, module expansion. You possibly need 5 or 10 sensors. Just increase sensor count. So I'm going to switch to the here it is. Just increase the sensor count macro in the sensor header file over here, and you will be able to extend function arrays. And one practical tip: in your main.c file you can use only one include. Okay, let's focus. You can use only one include, this one over here, include sensors.header file, and you will get full abstraction across all environmental sensors. This is how we scale NECTO-based embedded projects. And now I'm going to show you how you can test it yourself. Just jump in NECTO, just like I did it right now. Okay, after that, focus yourself on the planet debug feature over there. After that, make sure to search for the storm and quake alert string. And after that, connect to the transmitter node, not the receiver, but transmitter node. Okay, just click go over here. After that, you have successfully connected to the hardware part. Now let's focus on the software part. Focus yourself or navigate yourself to the package manager to download the particular software package. So once again, storm and quake alert, just type in that string over here, and make sure to download and open this transmitter software package. Okay, after that, you basically will have the transmitter node in up and running state. Then we need to configure the receiver node, right? Make sure to jump back in the planet debug feature and make sure to disconnect from the transmitter node. Of course, connect to the receiver node after that. And once again, focus yourself on the package manager, download the receiver software package, install it, and open it. After that, make sure to flash that particular receiver software package into the microcontroller. And as a result, the transmitter and receiver nodes are communicating between each other. But you may be asking yourself, I want to capture the data by myself, right? Okay, and now for the final demo, I'm going to show you Docker-based TCP server instance. Just give me a second. And just give me a second. Okay. And here it is. Perfect. Perfect, guys. And here it is. Here are the information. Here is the information that you are going to receive. And in essence, it captures all the data from the storm and quake alert receiver node. And by the way, the receiver node captures all the data from the transmitter node. And guys, this is how to get the job done with LoRa and Wi-Fi for early quake and flood warning with the help of NECTO Studio. Okay guys, and now we are on to the question and answering session. So please guys, ask anything you want to ask. Okay, so I'm going to answer question number 1. What makes the communication between the transmitter device and receiver device so reliable in this setup? Okay, cool question. Okay, I'm going to provide the answer right now. The system uses the LoRa 11 clickboard to handle long-range LoRa communication. The transmitter collects data from earthquake, from water detect, and from thunder clickboards. Then it formats the readings and transmits them using the LoRa 11 module. On the receiver side, the same LoRa 11 clickboard captures the incoming package, and which is then forwarded over the TCP UDP via the Calypso click. This two-step wireless link ensures both robust local transmission and flexible network delivery. Okay, I think that I have answered your question, but you have 2 more. Okay, question number 2. How does this transmitter solution manage multiple sensors simultaneously? Okay, good question. I'm going to show it once again, but within the NECTO Studio. So just give me a second to focus on the NECTO Studio. Okay, and here it is. Okay, here it is. The solution uses a modular design with an array of function pointers, and this is basically the sensor function funcs or something like, yeah, array of sensor data function pointers. Yeah, because of that, each pointer maps to a different sensor data fetching function, allowing the state machine to loop through them efficiently in runtime. So very important thing in runtime. Okay, that would be question number 2. Now I'm going to answer question number 3. Okay, can I swap out the earthquake or thunder click for another sensor without rewriting the core logic? Yes, definitely yes, and that was my main task for you guys today. This complete system is modular. As long as the new sensor has a compatible data fetching function that conforms to the sensor data function type. So once again, this type over here. Okay, it can be registered and used without modifying the state machine logic. Okay, since there are no more questions, I'm going to talk about this solution even more, and I will provide you with some kind of statements, and you keep asking the question, guys. Okay, I'm going to transfer to myself right now. Okay, cool. Okay, statement number 1. I have designed this solution to operate in harsh weather conditions, and that's why the thunder clickboard and water detect clickboards were chosen. They respond quickly to environment changes, and it provides me with timely data. Okay, another statement. What is elegant here is that all sensor reading logic is abstracted into modular functions. This lets me scale or swap sensors without touching the state logic in the application task functionality. Okay, another thing that I managed to do is I have chosen Docker, as I have previously showed you guys. I have chosen Docker to test the Wi-Fi connectivity. And while the Wi-Fi module, Calypso clickboard, isn't used in the transmitter role, its counterpart on the receiver side enables remote access, making this a complete IoT solution. Okay, let's talk briefly about throughput, network throughput, right? Each sensor transmits its data independently with a delay in between, ensuring the LoRa channel isn't congested and that messages are spaced out for reliability. Okay, and something more about reliability. When the system boots, it goes through power up, then config, then data transmission stages, and these are clearly separated in a finite state machine. improving both clarity and reliability. And what's also handy is that this transmitter solution shares the same main.c file, the main file, the main source file, with the receiver control purely via compiler flags. So you basically reconfigure compiler flags inside the CMake file, and that would be it. And that avoids code duplication and simplifies maintenance. Okay, something more about the logging. I used log printf functionality to give immediate insight into what's happening at each stage of execution. This is crucial during deployment or testing in the field. Just imagine yourself on some kind of a field and you would like to test this solution. And it would be wonderful if you had the logging enabled. And this is why I have implemented the logging part. Okay. Okay, something more about formatting the message. Each message is packed as a formatted string into a buffer. And I have used this function over here. I'm just going to show it to you guys. Yeah, I have used the LoRa transmit functionality, right? To send it out, to send the data out. And it's all compact, low power and robust. Okay guys, I'm going to wrap up this webinar with a couple of final thoughts. Just give me a second to transition to myself, okay? Okay, final thought number one. This solution is ideal for off-grid alert systems, especially in remote areas where cellular service is poor, but LoRa's long range can still reliably deliver sensor warnings. Okay, and the final thought number two, the system can be expanded. You can add more sensors, you can register their functions, their functionalities, and the state machine will handle them just like the rest. That's the power of abstraction here. Okay guys, if there are no more questions for me, I just want to thank you for watching this webinar, because I wanted to show you the power of modularity when you use NECTO IDE to build some real-world embedded solutions. And I have something for you guys. Just give me a second. Okay, here it is. Okay. Okay, the next webinar will be all about remote control cars, and this is why I have showed you, and yeah, I'm definitely going to send the remote or URL website to the next webinar session. And I think that we have a question, which is perfect. Once again, we have a question from Bob. Hello Bob, what drove you to do the define statement in the make file instead of the in-main.c file? Okay, good question. Yeah, because I want to automate every single thing. Yeah, I definitely want to make sure that source files that I'm using are clean and modular, because I'm dealing with the SDK approach, and I want the source code for every single development system that I'm going to use for my future webinar sessions. It is totally reliable, and it is totally modular. So this is why I want to make sure that the source code is clean, and this is why I have chosen to not modify the main.c file, but to modify the CMake list.txt file. Okay, that would be the final cause. Okay. Thanks for asking that, Bob. If you have some more questions, please do ask them once again. I'm just going to wait for a bit. Yeah, I have sent you a link to my next webinar session, to my next webinar theme, but I would like to send the promo page of all the webinar sessions that I'm going to deal with during this year. Okay, so just give me a second. And here it is. This link is all about the whole roundup of my webinar sessions that I'm going to talk about in terms of this year 2025. Okay, so please guys, do ask anything that you want. I'm just going to wait for a bit. Okay, I'm going to check whether there are some more questions. Okay, there are 3 questions from Oliver. I have already answered them. There is one question from Bob Hunt. Thank you, Bob, for asking the questions. And yes, okay. Yeah, Bob, no worries. It's kind of great having those webinar sessions. I like doing them because, yeah, I like electronics and embedded stuff and programming as well. Okay, I'm just going to wait for a bit. Okay, I think that's it, guys. I think that's it. Yeah, no more questions. Okay, with that being said, I will be seeing you in the next webinar session. So the next one is definitely going to be about remote control cars. Please do visit the link that I already placed during this webinar session. So please do get informed, and it is going to be an interesting one. So yeah, with all of those being said, I'm going to say goodbye. See ya.